Thank you.
Yes.
So today we've got Xiaotang. She's one of our own PhD students. She's in the process of looking for what her next step is. But I would say in the meantime, all of us could probably, certainly I could benefit a lot from learning more about what you're doing in the department. I know you do a lot of really interesting work on ride-hailing services, transportation services. So let's give a warm welcome to Xiaotang.
Thank you for the great introduction. Good afternoon, everyone. My name is Xiaotang. I'm a PhD scientist in Industrial and System Engineering Department at the University of Minnesota. My advisor is Professor Xiaotang. I'm very okay. Thanks. I'm very honored and excited to have this opportunity to present my research in our department. So, my research is in the area of operations management. I focus on the unmanned service platforms, smart mobility services, and the sharing economy. Specifically, my research aims to study the intervention of novel business strategies and innovative technology, how this will reshape the operations of those platforms and how this will in turn affect the workers and customers. For my research in the stream of novel business practice, I study the effects of two-sided competition on workers and customers. I also study how the pooling strategy for platforms motivated by a ride-sharing system. Also, I study how the service provider should, what kind of contract the service provider should sign with strategic workers. For my research stream in innovative technologies, I study how the introduction of fully or partially autonomous vehicles to this system affect the outcomes. Today, I would like to present our recent work, human-in-the-loop automation, mapping with remote drivers. This is a joint work with my advisor, and Xiaotang. So I believe everyone knows the idea of autonomous vehicles or self-driving cars, but it is increasingly apparent that fully autonomous vehicles may take longer than initially expected to become a reality. Technically, the current decision-making algorithms are not able to test all possible scenarios encountered in the real world and make safe enough decisions in a reasonable amount of time. Although the technical challenges can be solved in the near future, the public acceptance is longer. So currently, the concerns about safety continue to be high. There is a new technology, Tele driving, that combines vehicles that are partially autonomous with human operators. So this picture shows the idea of Tele driving. As you can see, Tele driver sits behind a bunch of springs with those conditions to control a vehicle remotely. Tele driving provides both the efficiency and the flexibility of autonomous vehicles, but by putting humans back in the loop, ultimately responsible for driving decisions. So Tele driving holds the promise of overcoming both technological hurdles and the societal concerns of driverless vehicles.
What's the gain from having them remotely rather than just sitting in the car?
I will, that's a very good question. I will talk about this in a few slides.
I think I was going to ask maybe something similar, like whether they're in charge of several different vehicles or
no, one Tele driver can control one vehicle at a time. But I will mention the benefits of the Tele driver. Teledriving is not just a concept. Many pilots are demonstrating the commercial viability of teledriving. For example, Lee and Hello in ride-hailing and car rental markets. Coco and Starship in food delivery system. Xiaotang also in warehouse logistics, and ISyE in market market. Next, I will show you a successful application of teledriving in food delivery system. So there is a company called Coco in California. It provides semi-automated robot delivery service to customers. Let me show you how it works. So once an order is placed, Coco dispatches an idle remote driver to control a bot to the location of the restaurant. And then at the location of the restaurant, the merchant will put the food into the box. And after that, a remote driver will control the vehicle to transport the food to the location of the customer. And then the customer can use smartphone to unlock the box and enjoy his food. So for Coco, to date, hundreds of restaurants and stores have signed up to use the service from Coco in Los Angeles. So for those companies built around teledriving, they operate with a pool of drivers, and drivers are not dedicated to a single vehicle compared to that in the conventional system. But instead, they can switch freely among any vehicle to control any vehicles in the system. So the teledriving brings in a lot of benefits. Perhaps the most important one from the operational perspective is that teledrivers can be viewed as a spatially pooled resource. Although vehicles are restricted by their geographic location, teledrivers can be interchangeably assigned to control any vehicles to serve customers regardless of trip origin and destination.
Sure. Let me see if I can get the benefit of having the teledrivers is that you can essentially teleporting the driver where he is to where he needs. Get the benefit from having the guy.
Yes.
For,
And another benefit is that compared with the teledriving is that compared with the conventional in-vehicle driver system, the system can the service can be operated with fewer drivers than vehicles. Any other questions before I go forward?
Driver like road control vehicle or like they're just like unlike like because those are already autonomous vehicle already. So what type of role has this driver like are they just like conversely are they on a good condition or like they actually operate?
In our model, the drivers have full control over the vehicle. So in this work, we study the effects of switching from a conventional in-vehicle driver system to a teledriving system by reducing the number of drivers. We aim to quantify the benefits of switching to the teledriving system with respect to the customer service level, customer delay, and the labor cost savings. In this work, we use ride-hailing as a motivating example of teledriving, but our model and analysis can be applied to other transportation network services like food delivery and warehouse logistics. So we consider a ride-hailing platform operates with N vehicles and N drivers, with the number of drivers being smaller than the number of vehicles. And we note that in a system where the number of drivers matches the number of vehicles, it corresponds to a conventional in-vehicle driver system. We assume that demand arises to the system continuously over time for a perform process with lambda. And the trip origins and destinations are uniformly drawn from the service region, which we assume to be a bounded and convex subset of R2. In our basic model, we assume that customers are impatient, and we will extend our analysis to the system with patient customers. So specifically, we assume that when a customer arrives to the system, if the customer is not matched with an idle vehicle and an empty car, the customer just leaves the system. Otherwise, the customer is matched with the closest vehicle and one of idle remote driver. Once the service is completed, the remote driver parks the vehicle where the service is terminated and switches to the idle mode to be ready to serve future customers. Also, the dynamics of the system. So if you think left-hand side remote driver, the driver is controlling the vehicle remotely to transport the customer. And for this right-hand side driver, after dropping off the customer, the driver disconnects from this vehicle and switches to control the vehicle that is closest to the arriving customer to pick up the customer. Any question about the second?
So, if you match the customer to the call, there's some time for that vehicle to actually drive to the customer.
Drive to the location of the customer.
But you're assuming that if customers match, they'll be willing to wait for that vehicle.
If they are willing, they are matched with the, they are willing to wait the vehicle, even the contact might be blocked.
So it might be very useful for you to have a slide where you talk about what they built the, like what do you, why would you be willing to wait right now? To clarify question.
My first question. So now you assume like once the driver controls the vehicle, there is somehow cash ticket, but the driver cannot switch to another vehicle for the end of the car. So it seems to me like the benefit of having more vehicles and the driver is just to take the time of moving the current vehicle to the other location. The coordination is like your vehicle finish the trip. Yeah. The driver can just switch to control another vehicle. So it seems like the benefit is only on saving the time.
Yeah,
from one location.
yes, right. Your insight is right. In some regions, but in other regions, with like the system, the vehicles in the system is not enough to fulfill all the demand. Then the teledriving could win other benefits. I will discuss more about that. Any other questions? Okay. So for customers who receive the service from the platform, the service time consists of two components: the pickup time and the actual travel time. The pickup time depends on the expected pickup time depends on the number of idle vehicles a customer arriving customer sees. Because we assume that customers are matched with the closest vehicle. So if there are more idle vehicles in the system, it is possible. It is more likely that the customer is matched with a nearby vehicle, so that the pickup time is short.
One thing I'm not understanding is, I have the car, it went to Dayton, deliver something, but it might be completely inefficient to keep it there. I may want to have to move it back to a location where it could be somewhere else. Where's that time going?
Oh, in our model, we can consider the relocation of vehicles. We just vehicles at a location where the last service. other question? Yeah, and also in our setting, because the demand of origins and mechanisms for demand are uniformly so from the first, so consider relocation. So, now let me show you how we characterize the expected pickup time. Consider the following facts. Suppose there is a two-dimensional space that is bounded and convex, and there is a set of K points denoted by the blue dots that are independently and uniformly drawn from the space. There is another uniformly drawn point from the space, which is independent from the set of K points, K blue dot points, and we denote this point by the red star. Then the expected distance from the red star to the closest blue dot is have the order of 1/2. Okay, so if you consider the idle vehicles in the system and those blue dots in the system, and the red dots the red star as the underlying customer in the system, then we can approximate the expected pickup time in this form is given by S divided by the root of the number of idle vehicles customer. Whereas in the expected travel time between two uniformly random locations. And we note that this similar approximations are adopted to study problems with stable features in the research, for example, flow, dispute, and chlorine.
So when trying to solve a real world problem, which we consider that the bottleneck is the number of drivers, and we're trying to solve that by increasing the number of cars.
Oh, the problem, the benchmark is that we have the same number of vehicles and cars, or the vehicles and drivers. And the Tele system is that we keep the same number of vehicles, but we're reducing the number of drivers. So we compare those two systems. We are not adding cars to the system.
So the advantage is simply reduction of cost.
Reduction of cost, but it will have other benefits, not just the reduce on the labor cost, but it will also improve the performance. I will example. Okay, any other questions? Okay.
Is this approximation exact when we're in a circle and everything like it's box one around?
Oh, so for this approximation, so here in the approximation, the numerator is S is the distance between two random locations. But actually, this is not exact. The exact form should be some other constant. It doesn't necessarily need to be S. But in this paper, by this is done numerical experiments and show that the constant, the right constant in the numerator is very close to S, and to simplify the analysis with S. But we can extend our analysis to other parameters, but it doesn't change the result.
Does it change with the geometry of your region?
It will change the yeah, it will change.
So the exact result is that we have that order of 1/2. That whole,
Yeah.
That's
Yeah.
always good.
the actual form and the value. Less amenable to analysis. Less amenable to analysis. So this is sort of simplified payment. And this is exact. And some special.
Okay, yes.
Advantage when we have pre-autonomous group compared with
Can you repeat your question? I didn't hear that.
how pre-autonomous flows, which can actually deliver to the exact. What is the advantage that we get out of this?
So your question is that if the amount will apply to like the law.
Yeah.
Yeah, we can do that.
Because
If we have two or three dimensional.
like we have limited, now in this case, let's say, like you have number of cars and number of drivers are equal. So in return also the driver has to drive the car, right?
Yeah.
So if we get approval when it is coming back, only one way has to be that, right? So number of vehicles are more and the number of drivers are less. So in return you don't need a driver, it should be a road.
Yes.
Because you don't need to give it to the exact delivery.
Yes, right, yeah. So, yeah, I think the amount can apply to the
This is very interesting. I have a couple of questions. So, just in case, so this is one order and one time, right? So for example, advanced star goes to what we got, and just there's a whole restaurant that also wants to practice will allow the drivers of the vehicle to pick up a second order.
So yeah, so you mean like we can like have some pooling strategy for the demand, but I think based on my knowledge for coastal, they do not pool demand because the capacity for the box is quite small. But also, I think it's possible to like pooling for the demand. And it's also very interesting research program to study in the future. Yeah.
My question is like, the one that open one is not supposed to be optimal. And it should be optimal.
Yes, I think someone showed that in the last committee consider. So in the last committee, the closest matching policy is almost optimal.
Finally, lastly, in order for this to be able to
Yeah, yeah. I think someone showed that in the last committee, the closest matching is almost optimal. Yeah. But yeah, maybe you have to idea.
And a lot of people is involved. So depending on where the next order is go up.
All right, because if the demand is uniformly distributed, then the close matching is almost optimal. And then moreover, we assume that the service time follows exponential distribution with mean 1 over UQ. Where Q is the number of customers in the system, and observe that the first term, colored in red, it captures the pickup time. So when the system has Q customers in the system, when the system has Q customers, then the number of idle vehicles and arriving customers is given by the number of total vehicles minus Q plus 1. And then the second term, colored in blue, captures the actual pickup. Because the pickup time is dependent, so the service time is dependent, and observe that the mean service time increases the number of customers in the system. It means that when there are more customers, the pickup time is longer.
Potential assumption. This was
That's for technical flexibility.
yes. So imagine if there was like based on station. The next one was, like there's more locations kind of far from than there are close to.
Yeah.
So,
But yeah,
you covered exponential, but still depending on the distance, right? So you'll still be more likely to have a big exponential than a smaller.
And the system can be viewed as a state-dependent queue with the rate, no queue. And the dynamics of the system of the first and second process. When the birth rate is given by lambda and the death rate is given by Q times mu Q given system has Q happens. With this, we can solve for the station distribution with Q number of customers in the system. And in a similar way, customers are turned away when all remote drivers are leaving. So the service level is defined by 1 minus the probability that the system has a new customer. Okay, any questions? Okay, before introducing our main results, I would like to use a toy example to illustrate some important insights in machine learning, which can also answer the question from you, like what is the benefit of having driving? We first consider the case when the supply of vehicles in a system is limited. So in a conventional system, it is likely that when a customer arrives to the system, the customer sees a limited number of vehicles. For example, in this plot, we use a white vehicle to denote idle vehicle, and we use a black vehicle to denote a vehicle being occupied. So if the customer sees a limited number of vehicles, it is likely that the customer is picked up by a borrowed vehicle, so the pickup time is long. This scenario is widely observed in the literature, which is referred to as the white goose chase phenomenon. The white goose chase phenomenon says that in equilibrium, if the service supply is limited, then customers are picked up by borrowed vehicles. And by switching to a high driving system and reducing two drivers, as you can see that the system always guarantees at least idle vehicles to pick up the customer. So finding a nearby vehicle is more likely, so that the pickup time is shorter. We refer to this as the shorter pickup time effect. Okay, any questions about this? Okay. Then we consider the case of the supply of vehicle is large. Then in this case, when customer arrives to the system, it's likely that the customer sees plenty of idle vehicles in the system. And the pickup time for this customer is likely to be short. Then by switching to a heavy driving system and reducing the few drivers, the same pickup time can be achieved. As the platform can assign a remote driver to control the vehicle that is close to the customer. So in this case, reducing the number of drivers does not affect the system performance.
So now, although we have like shorter pickup time, but in terms of the amount of demand, the system develops like second system.
Yes. So yeah, maybe I can jump to this slide. So by reducing the number of drivers, essentially there are two effects. On the one hand, there are fewer drivers in the system, which reduces the effective capacity of the system. On the other hand, because as we just introduced, reducing the number of drivers can reduce the pickup time. So this increases the effective capacity of the system. So the effect of reducing the number of drivers depends on the relative strength of these two forces. Then the question is, which one is stronger? The answer to this question depends on the operating condition.
So adding more drivers means take more rides.
Yeah.
But when you say pickup times,
average pickup time among accepted rides?
among accepted rides.
Yeah, can you go back to the first graphic? Not able to understand. So, yeah, this one is that. So here we're still considering that you have 3 idle vehicles. So how is like it's not the same system, it's not the same situation, right? Because
The system has the same number of vehicles, but in this system, we have only 3 remote drivers.
what if the other 2 vehicles were also occupied? They're not.
It is
idle
not
vehicles.
possible because I only have 3 remote drivers. So at most, 3 vehicles can be occupied. So a customer means that I have at least 1 idle remote driver, which implies that the system has at least 3 idle vehicles.
Okay, so again, coming back to the first question that I had asked earlier, so effectively is if we try to apply this in the real world model as of now, we're not going to reduce the number of drivers, but essentially increasing the number of cars, because the cars that we have already, we're not going to fire the drivers that are already working. It's that close to what we're trying to do. Because effectively we're going to increase the number of vehicles so that this model is viable.
You can think of that the system having more vehicles, but our analysis would fix the number of vehicles.
Well, yeah, the idea is actually to fire and drive because for the company.
But yes, you can like say that the company that very high drivers, but you know, professionally, so the number of drivers can improve the demand input. So like you have win-win, to have less cost, but to have more revenue. Okay, so we have these 2 counteracting forces, the fewer driver effect and the shorter pickup time effect. And which one is stronger, as I just mentioned, it depends on the operating regime. The operating regime is defined as the number of vehicles relative to the system workload. Depending on the value originally denoted by alpha, depending on the value of alpha, we distinguish 3 operating regimes. If the value of alpha is small, we say that the system is in the supply limited regime. And we say that the system is in the intermediate regime, the value of alpha is moderate, and we say that the system is in the supply rich regime, if alpha is large. And we know that the shorter pickup time effect is stronger when the value of alpha is small. Okay, so with this, our result shows that in the supply limited regime, reducing the number of drivers, surprisingly, it can actually lead to a higher service level. And in the supply rich regime, we show that reducing the number of drivers always leads to a lower service level. But the decrease in the service level can be negligible even with the reduction on the number of drivers is significant. Okay, this is our main results at hand, and then I will elaborate the results in each region. So in the supply limited region, we show that as shown in this plot, the service level can be first increasing and then decreasing in the number of drivers. So this result implies that so in general, people expect that the service level would be higher if I have more service capacity, but this is not true here. So this result implies that the platform can actually improve its service level by reducing the number of drivers. We obtain the necessary and sufficient condition for this to occur. And we know that this condition depends only on 2 parameters. The number of vehicles in the system and the system workload. So as you can see that this condition holds in general as long as the number of vehicles is not too small, for example, greater than 10. In this plot, we vary the number of vehicles and select the number of drivers that maximize the service level. Observe that the increase of service level relative to a conventional in-vehicle driver system is significant. This is because that in the supply limit region, as we just discussed, the short-term pickup time effect is strong and it dominates the hero driver effect. This leads to the increase in the effective capacity of the system, so more demand can be fulfilled. Any questions? Yes.
Give us some insight about the why. You see one monotone, right? Yeah, the one in the left. Right.
Yes, so because in the supply limit regime, the shorter pickup time effect is strong, right? It increases. You can say that it reduces the system workload because you don't need to spend a long time to pick up customers.
Imagine the room when the car arrives. The customer arrives and they're really far away from that car. If I have a driver and I dispatch the car, I'm wasting a lot of time going to pick that customer up. Whereas I'd rather just actually reject the offer, reject the customer, wait for another customer to show up who's closer to that car. But because we're assuming that we always assign someone as possible. If I don't have a driver to drive that last car, it's actually good for me.
I think that makes sense because from my perspective, I'm thinking that looks like optimal is 60 something. And from the platform perspective, let's say I have 8 drivers, just hanging out and doing nothing. So that really wouldn't be because they're not doing anything. That's 62 people working at drivers.
Right.
So that's why I'm thinking that why would managing people want to
Very far away. So that the compatibility is blocked by enough content. So it's a waste of content.
So having more people to solve.
I guess, Xiaotang, that works up to a point, right?
Absolutely.
Eventually, if you keep the same number of drivers, it will catch up with the structure.
Any other questions? So that's the result in the supply limit region. And then in the supply rich region, we can obtain the similar result as that in the supply limit region. That is, the service level can be first increasing and then increasing in the number of drivers. And the necessary and sufficient condition for this to occur has the same form as that in the supply limit region. However, we run numerical experiments and observe that the benefits, the improvements of service level to switch to a capacity quite limited compared to that in a supply limit region. We will discuss more about this in the other part of the analysis. Then in the supply rich region, we show that the service level always increases in the number of drivers. So this means that reducing the number of drivers would lead to the reduction of service level. However, as shown in this plot, we characterize a well-specified threshold Q star such that if the number of drivers is greater than the threshold, then the effect of reducing the number of drivers is negligible. In a high driver system, we can manage the capacity of vehicles and drivers separately. So reducing the number of drivers while maintaining the same number of vehicles has less impact on capacity than reducing both vehicles and drivers like that in the conventional system. This is because that in the supply range region, the platform can still use this large amount of vehicles to reduce customer pickup time by assigning a remote driver to control the vehicle that is close to the customer to pick up the customer, as long as the number of drivers in the system is not too small. Okay. And in the cost regime, we quantify the benefits of switching from a conventional in-vehicle driver system to a tele-driving system. So we fix the value of alpha, which is the number of vehicles relative to the workload, and we send the number of vehicles and the customer arrival rate to infinity. Then we show that switching to a tele-driving system can, in a supply limit regime, switching to a tele-driving system can save the service level by at least 1 minus alpha, where alpha is smaller than 1 in a supply limit regime. So what does this result mean? For example, if you have a system that the value of alpha is 0.5, then switching to a tele-driving system, you can improve and select appropriate number of drivers. You can improve the service level by at least. Then in the supply, in the intermediate regime, we show that the tele-driving system does not bring significant benefit on those levels.
Okay, so the supply limit is alpha between 0 and 1.
Yeah.
Next one will alpha between 1 and 2. That's the engineer.
Engineer. And in the supply range regime, the value of alpha is greater than 2. And we define this n minus star as the minimum number of drivers needed to maintain a similar, arbitrarily similar service level to that in the conventional system. And we show that in the supply range region, by switching to a tele-driving system, reduce the number of drivers by at least 1 minus alpha. Over 1 minus 1 over alpha. So for example, in a system in the supply limit region, then the number of drivers can be reduced in that half. Okay, any questions?
So in real life, it's like Uber or whatever. Do you know in which regime they're operating?
I think Uber is operating in the supply limit regime because the white machine can provide customer from several universities, capture the Uber data and indeed observe the white machine phenomena. But in the supply region, the white machine phenomena and the intermediary, the white machine phenomena would not occur.
So they
At least in particular, I think they are in the supply. In the supply limit, if the like for example in the 2 hours, like 5 hours.
yeah.
Do any headway about the quantum distribution over a couple of weeks?
In our analysis, for sensitivity, we consider uniform distribution. But I will.
Yeah, I know, I understand, I appreciate why you would need to do this. It seems foreign and difficult.
Yeah, that's I will show you that we actually the uniform distribution option is not needed for our code.
Okay.
But also you have some data. Like
Yeah, we have
raw
data. Yeah, I will show you the reference of our data. In that case, the demand is not uniform among the three. Okay, so far we assume that customers are impatient. They are not matched with the idle vehicle at the Amazon driver. And then we extend our analysis to the system with patient customers. So customers always within the system until receiving the service. So in this it is possible for the number of customers to build up to infinity, and we call that the system is unstable if that is true. Report that in the supply limit regime, which show that if customers are impatient, then heavy driving can significantly improve the service level. But if customers are patient, then the heavy driving system cannot fundamentally change the system because the system is always unstable regardless of the number of the driver capacity. In the intermediate regime, if customers are impatient, so that the heavy driving does not bring significant benefits to the system. But if customers are patient, then we show that heavy driving can stabilize an otherwise unstable system. So the benefits are quite large. In the supply rich regime, if customers are impatient, then we can reduce the number of drivers to maintain the same service level, and we get parallel results when customers are patient. That is, heavy driving can save a significant amount of drivers while maintaining the same customer delay. Question? Then to check the robustness of our results and quantify the benefits of a heavy driving system in a more realistic setting, we run numerical experiments using data from New York City. The data contains the time and location for each pickup and drop off. So in the simulation, we assume that each customer is matched with the closest vehicle. And the pickup time is approximated by the total time along the shortest path. And then the trip time is the actual trip time from the data. And then the location of which vehicle is updated with the trip destination. So we still do not do the location of the vehicle based at the location where the service is located. The numerical results is consistent with our theoretical results. Specifically, in the supply limit regime, the heavy driving system can improve the service level by up to 20%. And in the supply rich regime, the heavy driving system can reduce the number of drivers by 40%. To conclude, in this work, we studied the effect of switching from a conventional in-vehicle driver system to a heavy driver system. And we show that in a heavy driver system, by reducing the number of drivers, if the system is in the supply limited regime, then the platform can improve the service level or system performance by reducing the number of drivers. And in the supply rich regime, the platform can reduce the number of drivers significantly to maintain a similar system performance. Call for any questions? How many time I have?
It's 7 morning.
7 minutes is all. So with that, maybe I can introduce and briefly talk about another of my work. So in this work, we consider the introduction of fully autonomous vehicles. So there is a debate that whether the introduction of automation will benefit or hurt workers. Economic literature has identified two counteracting forces. The first one is the displacement effect, which hurts workers, and the productivity enhancement effect, which benefits workers. But those effects does not consider assessing that drivers are strategic. So this is of particular importance in a sharing economy or gig economy market, where drivers and workers typically decide whether to work, when to work, and how to conduct the work. So in this work, we studied the impact of introducing autonomous vehicles to a ride-hailing platform, and we study how will this affect workers. we show that the introduction of autonomous vehicles can actually benefit workers. On the one hand, the introduction of automation may displace workers, but on the other hand, the introduction of automation may reduce the inefficiency resulting from the selfish behavior of strategic workers. So as a result, the platform is willing to rely more on strategic workers to fulfill more tasks. That's the story for this work. Any questions?
What are the assumptions that? But obviously, if I can just support everyone with.
The assumption for me to get this is the cost of autonomous vehicle is moderate and the worker perspective.
So the cost of autonomous vehicles, but it's,
Yeah.
then obviously it's terrible for driving.
But if the cost of autonomous vehicles is very high, then platform, it is also costly for platforms to use autonomous vehicles to control, to influence drivers. So when the cost of autonomous vehicles is moderate.
There was a situation one in report. If I am during rush hour, I have all the incentives in the world to go every single time I take this upper rush right back to the city to pick more other people downtown. But then every single driver is downtown. I don't have anybody in the suburbs when the people might be moving across.
Yeah.
But there's another way to use it. I can use the autonomous vehicle in order to discipline the individual driver. I can replace him strategically. Say, if you do not provide these routes that I would like to go today, tomorrow I'll have automated supply the more higher rent places. But you can use the rent of automated vehicles in order to discipline dynamic behaviors. That's the other way to do it.
That's possible, yeah.
Version of that. That's how automation. Right. And it ends up being.
So, related to that question, so would you have, in that case, that everybody goes downtown at rush hour, would you have, like autonomous vehicles fill the gap left by those vehicles, or to go downtown and force the drivers to go somewhere else?
So like, so in our case, we have no model. And in particular, strategic workers not want to go to the culture. We prefer to wait at the loading location. Unless there are a lot of drivers waiting at the loading location. That's what push the location. But in general, I think people would not just locate to the hiding location.
Somebody in the other place that kills off the expected benefit from moving, and I can't, which is a very neat idea. Very neat idea.
You're moving drivers downtown, push their VR drivers, like autonomous vehicles downtown to push.
When we use autonomous vehicles, when we put autonomous vehicles at the load level, push drivers to relocate to the hiding. Any other questions? I can do some. So, for on-demand storage platform, customers are sensitive to the price of the and the workers are sensitive to the wage and how to pay only the customers. In this work, before we explain whether the entry of the level problem and will be and the answer to this question is no. Competition is on both workers and customers. is because we show that the work is different, such that all workers will choose to work on both platforms. This is referred to as multi-polling effect. The multi-polling effect diminishes the competitive advantage of platform game to recruit more workers to reduce customer delay. This will lead to a lower wage for workers and more customer delay. So thank you very much for I appreciate question comments.
First off, good job. It's probably like my seminar of the series so far. So good job.
Thank you.
One question I had in the sense of like tele driving, you know, you're dependent on a connection between the driver and the vehicle. Whereas in like autonomous vehicles, you can rely more so on like the local sensors built within the vehicle. So is there any like thought process going around about like the dependence on connectability between tele drivers and the vehicle as opposed to like the inherent like non-connectivity that for like a fully autonomous vehicle? Is there any like thought going around on that?
The question is that so maybe there are some technical issues for example, honestly, the vehicle it's a very good question. Actually, we saw because it's not and the real estate that that's the case. So that the daily driver, if daily driver will have a lower speed. So in the next step, I think we added the speeding parameters to the total speed of energy and I believe that we are respectful for the speeding parameter as long as the speeding parameter is not now are we not quality speeding. Thank you very much.
Yeah.
I'd love to get a chance to